Okay, so in this lesson, we're going to talk about graphing logs and exponentials. So let's start with exponentials. So do y'all remember if 2 to the x, is that going to be exponential growth or decay? Growth. How do you know that? Because we have a 2 here, and if you take 2 to any power, isn't it going to get bigger? The bigger the power, the bigger the number we'll get. So if let's make a t-chart here, and let's use some negative numbers and some positive numbers. So -2, -1, 0, 1, and 2. And we're going to do this without a calculator. So what is 2? Whoops, 2 to the -2. What is that the same as? 1/4. So we are going to plot the point -2 to the 1/4. What about 2 to the -1? 1/2. What about 2 to the 0?
1.
Yeah, anything to the 0 power, as long as it's not also 0, that's a 1. So 0, 1. Now this point right here, this point 0, 1 is something we're going to call a critical point, okay? Because even if this 2 changed to another number, we would still plot that 0, 1, okay? All right, what about 2 to the 1? This is a little bit easier. 2, and then 2 squared is 4. So we'll plot the point 1, 2, and 2 squared. And you can see that we have kind of a growth pattern. Now watch what I'm doing here. I'm going to connect these. And I know about my parent functions, but I also know that just based off of the ones I did, if I plugged in, say, -6, and I try to take 2 to -6, it's not 0, but it's really close to 0. Okay? Is there any way this result could be negative? Like, could we have a negative number in the y column based off of this? No, because 2 to anything should still be positive, even if it's small or big. All right, so let's look over here and let's answer some of these questions. Okay, first of all, x-intercept. Does this thing even cross the x-axis? No, so there's none. All right, what about the y-intercept? 0, 1. We'll write it as coordinates of points. What about the domain, thinking left to right? Yeah, -infinity to infinity, all real numbers. The range, though, is not all real numbers. 0 to infinity, and we know we always have parentheses on infinities, but would I have parenthesis or bracket on the 0? Parenthesis. Because there's no point, even the way I graph this, there's no point that actually hits the x-axis. It just gets really, really, really close to. It's basically like in behavior, but only on one side, okay, or horizontal asymptotes. Now, in this case, do y'all remember what I said the critical point was? I mentioned it. 0, 1. And I said it that because no matter what, if you had a to the power of x, where a was any number, now a can't be 0, all right? It has to be like a legitimate number. If you take a, the only point all of those share is 0, 1. So if I change this 2 to like 3, it would still look pretty much the same. It'd be a little steeper, but it'd look the same, and it would have that same critical point. That's like the fixed point on the graph. All right, now we're going to do the same thing with log. Now I do want you to change what's on your notes. I would like for you to go ahead and put base 2. There was no base there, so what base were these notes implying? 10. We're going to make it base 2 because I want to show you something. Oh, I guess I should write this. Other exponential functions include 3 to the x, e to the x, 10 to the x. You get the drift here. It's a number to the x power. Okay, so now let's do log base 2 of x. Now, keep in mind about how we've done logarithms, okay? And we're going to do the same values, -2, -1. Oh, sorry, that's not what I meant to say. Erase that. Okay, let's think about something that would be, that we can take log of. 2 to what power equals x? Okay, so 2 to some power equals x, or I could even call that the y here. This is going to take a little bit more critical thinking skills here to come up with this table. So I want to know, like if in this case it's probably easier to start with the y. If I let y equal -2, what's 2 to the -2 power equal to? We just did it up here. 1/4. So do you see how they switched around on us? Do you remember what type of functions have the x and y switching? What do we call those? Inverse functions. In exponentials and logs, they're inverses. The sooner we recognize that, the sooner I can just take the same table and flip-flop everything. Okay, so think of it like this. If y is -1, 2 to the power of -1 equals x. I'm just using that whole concept of rewriting a log to an exponent. All right, that would be 1/2. Okay, if x is 1, 2 to what power equals 1? Whoops, that's not what I meant to say. I keep getting mixed up myself, y'all. That's Monday for you. One. See how it switched around? It was 0, 1 here, now it's 1, 0. So what would you write next? 2, 1. Even if you're like, I have no idea what we've done, just follow the pattern. I'm just switching the numbers. 4, 2. So these points are going to be a little bit different. Okay, 1/4 now as the x is right about here, and then -2 would put us right there. 1/2 -1, 1, 0, and so on. I'll plot all these points. And I get a similar looking graph. Instead of a horizontal asymptote, what type of asymptote do I have now? Vertical, at x equals 0. And this kind of continues to go up and out forever. One last thing to kind of mention about these two graphs is they're reflections of each other across the line y equals x. And you did that before as well. So this time I have an x-intercept of 1, 0. And what's my y-intercept? None. So see how it switched? What about the domain? You think about, where does this graph start on the left? It starts at 0, again parenthesis because of the asymptote. It goes to infinity. But the range, however, goes bottom to top forever and ever. So the range is -infinity to infinity. And the critical point on this one is 1, 0. Okay, so I'm going to kind of scroll it up just a little bit so you can kind of compare the two. Basically, just everything switched. That's because these two things are inverses. Okay, and these are what we call our parent functions. Now, the little points here and there are going to change depending upon which log you do, but that critical point is going to be true for all logs. So we did log base 2 of x. We could have done just log x. What would be the base implied there? 10. What was the log base e? What did we call that? Natural log, ln x. And of course, you could do any base you wanted. Okay, they would look slightly different, steeper or skinnier, or wider, or whatever you want to call it, but they would still have the critical point of 1, 0. And they would still have the same general shape. Okay, you need to know these parent functions because what we're about to do is transform them. All right, now whether or not you're dealing with exponential or log, okay, when you change just the x, when you do x plus or minus something, does anybody remember just in general what that does to a graph? Like let me just give you a for instance. Here's the parent function for quadratic. What does this do?
Or makes it a fraction.
Yeah, let's expand this a little bit more. It moves in a certain direction.
Left or right, right?
Left or right? Which one for minus?
Right.
It moves it to the right one. So the same thing is going to happen here. When you have a little h, whoops, I don't know why this isn't writing anymore. That's fun. Hold on. Never fails. Okay, so H determines then a horizontal shift. This would be left or right. And remember, that's always opposite of what you'd think. If it's like minus a number, that's right. If it's plus a number, that's left. And we've studied that. So what do you think type of shift would be for K, which is off to the side? What's the other? Vertical. This would be up or down. So just to kind of give you a frame of reference, this would be like when we had parabolas, x squared plus 4. That would be up 4. Well, you can have the same thing happen to these. Okay, besides shifting left, right, up, and down, what else do we do to parent functions?
Like stretching.
Stretch, yeah, vertical stretch or horizontal stretch. So if with this C that's out in front, it can be either one. That's going to be a vertical stretch. It could also be the other one, which is a shrink or a compression. Okay, if the number in front is a big number, that's going to be a stretch. If it's a small number, that's going to be a compression. You may be thinking, why aren't we doing horizontal stretch and compression? We're just not, because none of the applications really use that. But we could have been, but we're not. All right, we could also use the words wider or narrower here. But all right, so let's look at number 1 on the next page. So the first thing is we've got to remind ourselves of what was the critical point of just the parent function 2 to the x. 0, 1. Okay, that's where you're going to start. Now, here's the deal. I'm using pen up here, but I can erase mine. Okay, you are hopefully using pencil. If you are using pen on your paper, I want you to write very lightly, because what I'm about to draw is our starting place, but it is not the final answer. Okay? So I'm going to start, and I'm going to do a lot of erasing as we go. And hopefully you are doing that. If you don't have a pencil out, I would encourage you to have a pencil instead of a pen for today's lesson. So the critical point will always start for exponentials at 0, 1. Now, if I shift this thing up, down, left, or right, that's going to change. That's what the eraser is going to be for. Okay, so our graph looks something like this. Now, the good thing about these is we don't have to be super picky. Remember how we made a T-chart on the front? This is pretty good, all right? Another thing is, let's go ahead and draw in that asymptote. This is only going to help us, okay? So this is where we start. What I've graphed right now is the graph of the parent function 2 to the power of x. So we got to think, okay, well, what's happening here? Well, what are the transformations? Well, let's start. This 2 right here, by the way, is just the parent function. All right, that 2 is not doing anything. The x minus 1, what is that going to do? It's going to move it to the right 1. All right, and the 3 is going to do something. For this first example, we're not going to do everything at once. We're just going to do one thing at a time. So if I move that point to the right 1, now it's right here. What if I moved the vertical asymptote to the right 1? Or the horizontal asymptote, sorry. Yeah, that's not really going to change. If you move a horizontal line to the right, it stays the same. So look what I have now. So this is where I'm going to use my eraser. My eraser's too big. Here we go. Okay. Okay, so that took care of the minus 1. What is the plus 3 going to do?
Move it up.
Up 3.
Is it only like opposite for?
Yeah, it's only going to be opposite for that horizontal shift. So now I'm going to move it up 3. So my critical point was at 1, 1. If I move it up 3, it's going to go 1, 2, 3. And what happens to my horizontal asymptote if I move it up 3? I mean, yeah, it shifts up 3. Kind of answered my own question there. So it's now at y equals 3. Now the whole reason we do that is so that I know the right side of my graph is just going to continue to go up. All right, but the left side should follow this asymptote. And if you don't shift the asymptote up, you may not know like how the left side of this graph is going to go. Okay, so there's your graph right there. Now at the bottom, it's going to ask us for the critical point, and what it's asking for is like your final critical point, which is that thing right there. So what were the final coordinates here? 1, 4. Now I'm going to show you a really easy way to check this, and this is going to help you know if you totally messed up or if you're on the right track. Okay, if you plug in 1, what's 1 minus 1?
0.
Duh, 0. What's 2 to the 0?
1.
1, and 1 plus 3 is? There you go. You checked your work. Okay, what about the domain? This is true for all exponentials. Domain is easier. Negative infinity to infinity. So the domain did not change at all for exponentials. Do you think the range changed at all? Yeah, it was 0 to infinity because we started at the x-axis, but since we moved up 3, we got to start at 3. Okay, now we've done all of this without the calculator. Okay, it's really actually very easy to use your calculator to check these. And I probably won't do it on every problem, but we'll do it on this first one. So go ahead and get your calculators out if you have it, and we'll plug this in. To get that exponent, you got to do caret. And if you have the updated system, it'll look like this. If not, you may have to use parentheses. But make sure that x minus 1, make sure all of that ends up in the exponent, and that the plus 3 is not in the exponent. And then these grids are 10 by 10, so I'm going to do a zoom 6. Now, it may not look exactly like ours, but you can kind of use the trace button and get all the main points. Like you can go and you can hit 1, enter, and it should say 4. So that's a really good, easy way to check that as well, okay? All right, so let's do a log one. Now the fact that this is ln should not throw you off. It could have said log. We're going to do the problem the same way. All right, so we start with the critical point. What was the beginning critical point for log problems? Not 0, 1.
1, 0.
1, 0. So let's plot that point. Let's plot the vertical asymptote. And let's plot a log. Now don't worry about how steep this should be. Okay, just make it just standard. All right, this is where the sketch part comes into play. Don't make it really steep though, or really flat, just normal. All right, so that's the parent function. What I've graphed is natural log of x. What I need to do now is you always start next to the x, and you work your way inside out. That's the order that you need to go. So we start right here with x minus 2. So what transformation would that be? Right 2, yeah. Right 2. So let's move the vertical asymptote right 2, and let's move the point right 2. And I'm going to erase just so it's not confusing, and I'm going to encourage you to do that. If you want to leave it on there lightly for comparison, that's fine. Your final answer, though, should be distinguished from your work, like bolded or a different color or something. Okay, so we didn't have this on the last one, but here we have a minus 3. What is that going to do to the graph? It's going to flip it across which axis? The x-axis. So the negative is going to reflect. It's going to reflect over the x-axis. Okay, so, and what is the 3 going to do? Where these are kind of acting at the same time. It's going to make it a vertical stretch or compression. Which one do you think? Stretch. It's going to be a vertical stretch, which would make it more steep. Okay, so watch what I'm going to do. The asymptote isn't going to change. If I flip this thing over on its head, it looks the same way it looks right now. The point is on the x-axis, so that doesn't even change. What's going to change instead is this. And because of the 3, I'm going to make it like steeper. So watch what I'm going to do here.
Shouldn't the point be down +1?
Well, I haven't got to that part yet. But yes, the +1 is going to change, but I'm going to do that last. As you practice this, you may be able to do some of these things more at a time. I'm just taking one thing at a time. All right, it doesn't have to be pretty. I'll do the last one in yellow. So then the very last thing we're going to do is this +1, which would move this up 1. Now again, that's not going to change a vertical asymptote. If you move that up 1, it's still in the same place. Is it going to change the point? Yeah, it's going to move up 1. All right, so here's that part. And the rest of this, I'm going to kind of, hold on. There you go. I'm still going to graph this, but it's clear that that critical point is now up here. And it's still flipped, and it's, excuse me, it's still really steep. It doesn't even really look quite like a log function anymore. It's pretty steep. If you were like, I did this, but mine doesn't look as steep, it's still pretty steep, but it's only like this steep, that's fine. This is a sketch. It's not like we're graphing these for NASA or something, okay? So it's still a sketch. What we're looking for is you know the transformations, and the biggest thing is down here, you know where your critical point is. So you start at the origin, 1, 2, 3, 1. So that critical point moved over to 3, 1, and we're going to check it, okay? So we plug in 3 back in for x. And what is, so 3 minus 2, that's 1. And everybody, what's natural log of 1?
0.
0. You guys did really good on that on the quiz. So natural log of 1 is 0. 0 times -3, that's still 0. And 0 plus 1 is 1. So easy to check. Okay, domain, you just look at your graph. It looks like we start now at 2 and go to infinity. And for log is all real numbers. And then we're just using the calculator here to check our work. Okay, this is all stuff we should be able to do without the calculator. You can just plug it in, check the work. Whoops, I did something wrong here. Oops. Hold on just a second. Whoops. You can tell it's Monday. Here we go. And so see, mine was a little steeper than theirs, but again, that's the whole sketch part. Notice your calculator, though, does not graph asymptotes. So that's something you're going to have to do on your own. Okay, what was the question again? What was your question? Yes. So anytime, I'm going to have you guys try these next 2 on your own, and then we'll come back. Keep in mind, you're going to do horizontal shift first. Then you're going to do, if there's a vertical shift or reflection, you'll do that second. the vertical shift, up or down, is always going to be last. Okay, let's go over what you guys have so far. If you're not quite done, that's okay. Hopefully you've at least tried parts of either one of these. But what's the critical point of exponentials? Like, what do you start with? 0, 1. So that's what you would do here. You'd plot 0, 1, and you'd make a little exponential growth graph. Okay, and your asymptote would be right here. This is what we call the parent function of exponential growth. Okay, exponential. And I know that's exponential because x is in the exponent. Okay. Then we start up here. Remember, we start right next to the x. We have a plus 5. What transformation does that do?
Left.
Yeah. So we're going to take our graph and we're going to move everything over 1, 2, 3, 4, 5. And the asymptote would actually not change. If you're like, why does the asymptote sometimes change and then other times it doesn't? It just has to do with a horizontal line. If you shift it horizontally, it stays in the same spot. If we had shifted that up or down, it would change, and we'll see that in a minute. Okay, that's the first thing. Okay, the second thing is we deal with any numbers that we're multiplying by. And we're multiplying by -3. So we have a reflection. And do you remember where you reflect over? The x-axis. And then we also have a vertical stretch. Both of these are being caused by the 3, the negative and the 3. So, first of all, let's reflect over. Okay, so if I reflect over, my point would be right here, right? And my graph would be kind of like mirrored. If I stretch it 3 times, instead of only being 1 away from the asymptote, well, how far would it be? Times 3. So that's a 1. It's not down 3, it's times 3. This is, I think, the harder part of these types of problems. But I'm going to give you a really easy way to check this in the end to know if you did it right. So we had a point up here, we reflected it over, and then we made it 3 times as far away. Stretched it out. Okay, then we have -4, which is the very last thing. That's going to go down 4. So this point is going to go down 1, 2, 3, 4. And the asymptote is also going to go down 4. Notice that this point is still 3 units away from the asymptote, which is lines up with my vertical stretch. So that's going to happen, and it's a good way to check. And I'm going to erase all this other stuff. All right, it looks like our critical point, if I just follow this, -1, -2, -3, -4, -5. And then -1, 2, 3, 4, 5, 6, 7. And I'm going to check this because this was a lot of transformations. We really could have messed up. So if I plug in -5 in for x, look at what happens. -5 plus 5 is 0. What's e to the 0? 1. Times something is still 0. Ooh, I messed up here then. Oh, no, sorry, 1. E to the 0 is 1. Times -3 is -3. And then -3 minus 4 is -7. So we did that right. I told y'all this was the hardest one. I'm in it. What about domain? It's true. It's the same for all exponentials. Like, even if you had no idea how to do anything else in this problem, you should be getting domain of exponentials right. It's all real numbers. And then the range here, the bottom this time would be -infinity, and the top would be negative, what? 4. It'd be wherever that asymptote is, and notice right up here, this number lines up with that. That's not a coincidence. That's going to happen. Okay, The last one is actually the easiest one. We need a break because that last one was kind of weird. So first thing for logs, remind me, what's the critical point? 1, 0. And so our parent function looks like this. The more you draw this, the better you're going to get at it. And then I only have one transformation. I don't have any left or right. Okay, I don't have any stretch or reflection. I just have up 1. That's not going to change my asymptote. It is going to change that point. It's not going to really be any steeper. It's going to just keep the same steepness. And that went to 1, 1. And here's your domain and range. Hopefully you were able to get that because this was a pretty easy one.
So what makes the range is always negative and then
Yes. For exponentials, domain is always all real numbers, and for logs, range is always all real numbers. Correct.